This video is meant to supplement videos that discuss finding volumes of regions that are revolved either about the x-axis or the y-axis using the cylindrical shells and the disk and washer method. It's mostly a problem-solving kind of video. So we'll do the same region in all four of the problems that we do. We'll just change the axes that we're revolving about. So our first example, we are looking at the region bounded by y equals x cubed and y equals the square root of x. And we're going to take that region and revolve it about the x-axis. So it's the same region in all four problems. Let's go ahead and draw it for the first time here. So there's the origin. When x is equal to 0, x cubed is also 0. And now when x is equal to 1, x cubed is also 1. As x gets larger, this is a concave up kind of graph. So there's y equals x cubed. Y equals the square root of x, on the other hand, has the same 2 points, 0, 0, and 1, 1, but it looks more like this. These aren't perfect graphs, but they'll do. And so the region we're discussing is this region in the middle. It's the region bounded by the two curves. The cube function does extend to the left of the y-axis. The square root function does not. Okay, so we will take a rectangle. We're going to revolve it about the x-axis. Because these are already in terms of x, x cubed and the square root of x, because they're already in terms of x, I'm going to keep them in terms of x, which means when I draw a rectangle, I'm going to draw one that is skinny in the x direction. So tall and skinny. Okay, so we're going to revolve this rectangle about the x-axis. Again, I like to reflect it over the x-axis first to see what kind of shape I end up with, and then I imagine just revolving about here. So when I revolve it, I'm going to generate a circle and then keep revolving it after I've made it halfway around. So back here, we'll have the same sort of thing. We'll be super fancy about this. Okay, and so up here we have this, and like so. And so there is well, we have to identify it. We would call this a washer. It's a washer because it looks like a disc, but we have this void in the middle that has been cut out. And the way we do this, because it's like a cylinder with a disc cut out, we use the disc method and then do this subtraction to actually perform the washer method. Our basic formula for the disc method is volume is pi times the square of my radius times the height. That's the formula for the volume of a cylinder. So we're going to do two of these. We're going to do an outside volume. What do I mean by the outside? That's the larger radius, which I'll draw here in a moment. And we need an outside radius for that. And then we're going to do an inside volume, which is the inner radius squared times the height. Oops, and I need a little pi out front. Okay, what do I mean by outer radius and inner radius? Well, the outer radius is the distance from the axis of revolution all the way out to the top of that rectangle that we're revolving about. So this is my outer radius. The inner radius, I'm going to draw it over to the left here. The inner radius is from the axis of revolution up to the end of the hole. Here is where our hole ends. Okay, so that's the inner radius. Now, again, think about which direction we're moving. We are moving vertically. If you move vertically along a line, your x value stays constant, but your y value changes. We start at y equals 0. We end up here at y equals whatever the value is on the top curve, and this curve is x comma the square root of x. So the y value is radical x. That's my outer radius. On the other hand, a point down here at the bottom for the inner radius, we start at 0. We move our way up to this lower curve. This is the point x comma x cubed. Now it might seem kind of odd that x cubed is less than the square root of x, but remember we are between 0 and 1. After we get past 1, then x cubed takes over as the larger of the two. The volume of this will be the outer volume minus the inner volume. And we tend to put it into one integral, and I want to caution you when you do this. It's okay to do it. So all of them have a pi in them, so we'll take the pi, we'll factor that out. We're going to do the integral. Now here's one slight problem with this particular example. We start at the point 0, 0, we end at the point 1, 1. We're going from x equals 0 to x equals 1 because we are integrating with respect to x. Okay? So I'm not going to put it all together. I'm going to show you what we would do in general. We will do the outer volume, which has the outer radius squared times h, minus the inner volume, which has the inner radius squared times h. If you factor out the h in our case, I haven't labeled it here, but the h is the thickness of that disk, and it's a left to right measurement, and so that's going to be dx. Our thickness is dx. Okay, so we can factor out the pi, which we have done. If we factor out the h, we're factoring out dx, which we're going to put here at the back end. And that would leave me, now remember we factored, we're going to take the outer radius squared minus the inner radius squared. So we'll have the integral from 0 to 1. The outer radius we said was the square root of x. That would be squared, minus the inner radius, that was x cubed, square that, dx. And one last simplification, I said we weren't going to solve these integrals, but I'll get it set up so you're kind of ready to. The square root of x squared is x, minus x cubed squared is x to the 6th. Okay, so that would be the volume. We can use ordinary integration techniques in order to evaluate that integral. For our next integral, you probably can guess it. We're going to revolve this same region about the y-axis. So let's draw the region again. Here are the two graphs, the same region once again. Now we're going to revolve it about the y-axis once again, and I'm going to do this with all 4 of my problems. Once again, since it's already given to us in terms of x, we'll keep it in terms of x unless we need to change it otherwise, and we won't in these examples. So again, a tall, skinny rectangle, like so. We're going to revolve it about the y-axis. Well, that means we need to draw the mirror image of it on the other side of the y-axis. This arrow is going to serve 2 purposes for us. One, to figure out how far we are away, and the other as we calculate something else later. But we're going to have that same rectangle over here. And if I imagine lifting this rectangle off the page and moving it around, we end up with a cylindrical shell. So we'd have that shell back in the back there. Okay. With the cylindrical shell method, we imagine slicing the shell wide open. Oh, I missed a part of my shell. That's why it didn't look right. There we go. We imagine slicing it open. I like to imagine slicing it open right where I drew that rectangle over here. When I do that, that produces for us a long box. Box-ish. It's a little bit tapered, but that's okay. Or beveled, I think is the more appropriate word. But the shading over here kind of matches the shading that's there. So that means that this dimension is dx. The height of the rectangle is the distance between the top and the bottom curve. Well, the top curve is the square root of x. The bottom curve is x cubed. When I'm moving vertically, the larger y value is the one that's on top, which means that square root of x is the one that's on top. If I want to find the distance between 2 points on a vertical line, I just take the difference of their y values. So this distance is the square root of x minus x cubed. So that's sort of the height of that box. Also, you'll remember that in order to find this distance really corresponds to the distance around the cylinder. When you go around a circle, you're talking about the circumference. So the circumference is going to be 2 pi times the radius. We just need to figure out what the radius is. And this is where my blue arrow comes into play again. My blue arrow went from the axis of revolution out to the rectangle. My rectangle has a coordinate of x comma y. If I'm moving left and right, but staying at the same height, my y value remains the same. It's my x value that changes. We went from 0 out to x. So my radius is x. So we complete this. This is 2 pi times x. And now we're ready to put it all together again. Once again, we are varying between 0 and 1 in the x direction. We are also varying between 0 and 1 in the y direction, but because I'm integrating with respect to x, that's not terribly important. Our volume then is 2 pi times the radius. I'm going to stick the integral sign in front of the radius, but my radius we determined was x. So we've got this part covered here, 2 pi times x. That part is covered. We multiply that by the height of the rectangle, which is square root of x minus x cubed. And then we multiply that by the thickness of the rectangle, or of the, not the rectangle, but the box, which is dx. So I'll have a dx out back. Now, if you want to get it set up, and this is for your practice only, I would suggest pausing it here and then trying to write it in an integrable form. Now, before you do that, I forgot to put my limits of integration, so it would go from 0 to 1. Okay, so we'll have 2 pi times the integral from 0 to 1. When we multiply x by the square root of x, we'll end up with x to the 3/2 when you add the exponents. And x times x cubed is x to the 4th. For our third example, same region. Where are we revolving it about this time? We're revolving it about the line y equals -2. Y equals -2. That's a horizontal line. It's a horizontal line, correct? Because it's a horizontal line, let's think about what that is parallel to. It's parallel to the x-axis. So in a sense, this is going to be like doing it about the x-axis, which makes me think that it's something to do with the disk method. Okay, let's check that out. Let's draw it and see how we go. Here is the region once again. I've drawn in also the line y equals -2. A little bit sloppy there. Okay, so once again, I see that this is parallel to the x-axis. Here's my x-axis. We'll draw a rectangle, thin in the x direction, and this one is almost completely disastrous. Let's see what's going to happen when we reflect this. We need the same distance from the axis of revolution up to that rectangle. That, for this particular example, is, let's see, about 1, 2, almost like 2 1/3 away from the axis. Okay? So, if we go down here about 1, 2 1/3 below, we're going to end up with a rectangle that looks like this. Okay, so we have to connect these two guys. This one comes out like so. Okay, so because our axis of revolution is so far from the region, it's going to have this gigantic hole. And if you really want to be, have a nice picture, there we go. Okay, so disk or washer, disk or washer. Well, because I'm revolving about a line that's parallel to the x-axis, and all of my stuff is in terms of x, problem-solving strategies have told me that I'm going to do it with respect to x, but let's think about what that's going to entail. The thickness here is dx, and what we have is we have this gigantic, this enormous disk with a hole cut out of the middle. Here is the sort of the surface of that disk. And we've got this hole cut out of the middle that we have to account for. So as we did this before, because it was the disk and washer method, our basic formula was volume equals pi times the square of my radius times h. We know that h is equal to dx in this case. It's sort of the thickness of the disc or washer that we're dealing with. How about the r? Well, remember we did the outer radius squared and the inner radius squared. The outer radius, remember we measure from the axis of revolution out to the top of that rectangle. The top of that rectangle is way up there at the square root of x. So there we start, we're up at y equals the square root of x. Down here, we're at y equals -2. So the outer radius is going to equal the square root of x minus -2, which is the square root of x plus 2. On the other hand, the inner radius is the distance from the axis of revolution here up to the bottom curve. And our bottom curve was y equals x cubed. So the inner radius is x cubed minus -2, or x cubed plus 2. So these are our two radii. Radical x plus 2 is my outer radius. Radical x, or x cubed plus 2 is my inner radius. And we will subtract them after we square. A very common mistake is to subtract them and then square them. Our volume, let's do this in black. Our volume is pi. Our limits are still 0 to 1. Pi times the square of the radius times h. Our h is dx. Now our radii, I need a little more room, so let me erase that first parenthesis there. Our radii are kind of messy. The outer radius is what we'll do first. Radical x plus 2, we square that, minus the square of the inner radius, x cubed plus 2 quantity squared. If you want to evaluate this, and I'm not going to do this, you would want to square out both of those terms, subtract the result of squaring out radical x, or x cubed plus 2 squared, subtract that from this. I can see that you'll have a 4 from 2 squared and another 4 from 2 squared, but they're subtracted, so those will go away. But I don't think there will be much else you can simplify beyond that. Once you've done that, then you can find the antiderivative and go from there. Our final volume may be the most challenging of them all. We'll see why in just a little bit. I'm going to go ahead once again and draw the region, and this time notice that we're going about the line x equals 4, which is a vertical line. Vertical lines are parallel to the y-axis. Because the axis of revolution is so far from my region, I'm not going to be able to have enough space to draw the other side of it, but you can imagine where it's going to go. All right, we are, once again, as I said, revolving the region about a line that is parallel to the y-axis. Because my function is in terms of x, and I'm going about the y-axis, or one that's parallel to the y-axis, it's customary, or it's kind of forced to use shells, unless we switch so that each of these are functions of y instead, but we're not going to do that. So let's draw our rectangle one last time. Okay, as I said, we would imagine having a mirror image of that rectangle way on the other side of that axis of revolution, but it's, again, it would be such a small picture, I'm not going to go ahead and do that. We have a thickness dx, and so we will revolve this. And again, you kind of have to imagine it off to the side there, but it's going to look something like this, and that's sort of the outside of the circle there, and then it starts coming back. And here's the bottom of that cylinder, like so. Here is the front edge, and now we're getting things confused with our picture. It's going to look something like that, and like that. And because it's so far out, we probably would be able to see sort of the bottom of that cylinder on the way out there. we're using shells. Shells, we need to know the thickness, okay? So that's the dx that's there. Again, remember, we're going to end up with some long, thin strip here. This shaded rectangle that we have depicted, one of the dimensions is dx. As before, the height is going to be the difference between the upper function, which is radical x, and the lower function, x cubed. So this is radical x minus x cubed. Finding the radius is the challenging part. The circumference is 2 pi times the radius. Again, remember this. The radius is the distance from the axis of revolution here out to the rectangle that we're dealing with. You want to think about the rectangle as having x and y coordinates there. Okay, so we're integrating with respect to x, right? We have the dx. So there's my dx. So my radius has to be in terms of x. Which way are we going for our radius? We are moving left and right. If we're moving left and right, our x value is changing while our y value remains the same. Out here, we are at x equals 4. Back here, well, okay, we're kind of at x equals x. So we're going from x out to 4. 4 is the larger of these numbers. 4 is always greater than the x value that's there. So my radius is going to be the larger x value, 4 minus x. Our circumference then becomes 2 pi times 4 minus x. We now have 3 quantities. We have the thickness, dx. We have the height of the rectangle, radical x minus x cubed. And then we have the circumference, which is this 2 pi times 4 minus x. Put that all together and we'll get our integral. We will still have the limits from 0 to 1. So our volume is 2 pi times the radius. Our radius we decided was 4 minus x, multiplied by the height of the function, that's the radical x minus x cubed, and then multiply by the thickness dx. We have, again, evaluate from 0 to 1. If you want to evaluate this integral, the next step, and I'll do that and then just leave you with that, the next step would be to multiply all of this stuff out. So we have 4x to the 1/2 minus 4x cubed minus x to the 3/2 minus plus, that is, x to the 4th dx.